My name's Gabriel, and this is Micro UAV Team Blue.
This is our micro UAV team where we are the blue team, and I'm Joel Garrido. I'm one of the team members. The other following team members are Ebin Thomas, John Kauffman, Gabriel Harf-Levy, Christopher White Boyd, and Lawrence Coffey. My role for the senior design team project is that I worked on the propeller placement and the payload placement for the fuselage of our UAV. Ebin Thomas's role is that he calculated the stress on main spars, and he would also decide the manufacturing method choice on the wingtail section and on the control surfaces. John Kauffman's role for this project is that he did the lift and drag calculations, and he did the 3D CAD simulations on the wingtail sections and control surfaces. Gabriel Harf-Levy's role for this project, he did the ailerons and elevator placement on the wingtail section. Christopher White Boyd's role in this project is that he did the electronics, energy storage, and the purchasing for this UAV. And Lawrence Coffey, he did his role for this project. He did the body and fuselage options. Over the past few months, the team has been constructing the UAV at John's garage, depending on the availability of the team members. Fortunately, every team member had the chance to participate, contribute, and experience in developing the UAV.
The objectives of our project was to make a micro UAV powered by an electric pusher-style propeller. None of the criteria was that it had to carry a 32-ounce bottle. Our goals were to maximize range and endurance. Our specific goals were to reach a distance of 45 miles and a flight time of 180 minutes with an aircraft under 12 pounds, while reaching a cruise speed of 30 miles per hour. This is the main reason why we created a plane with a low aspect ratio and a large wing. What motivated us to see the project through was mainly our cohesiveness as a team. Communication with each other helped us set expectations for each other. It helped us to see realistically what amount of effort each member could make. With that, we then all agreed that in-person meetings should be used more often despite the risk posed by COVID. The in-person meetings where we truly got to know each other and how we built better friendships. We all agreed to stick together till the end, in success or failure.
Our group's motivation to focus on the micro UAV project was an overall collective interest in aeronautical engineering, design, and manufacturing. Our team was motivated to produce the best UAV possible with the budget provided. The goal of this project was to design and create a UAV that can carry a payload for extended periods of time and over extended distances. The capabilities of our UAV would be tested in a competition against other teams. This competitive aspect of the project also motivated the team because every member wanted to achieve first place in this competition. The possibility of improving on the traditional UAV design was also a source of motivation because it gave us the opportunity to potentially aid emergency responders with a simple but effective design. Having a chance to apply all the education and skills acquired during our coursework to an actual engineering project was also a source of motivation.
As the initial requirements of our UAV were to carry a payload, we imagined this payload as being something along the lines of a camera, thermal imager, and GPS. This would make our UAV an economical solution for disaster relief and search and rescue. For disaster relief, design considerations included how to maintain maneuverability in harsh conditions with the attached wireless camera and GPS tracking payloads. We also looked into possibly carrying something along the lines of medical supplies to hard-to-reach locations. The UAV needed to be capable of handling extended flight times and be durable enough to survive multiple takeoffs and landings. The design of our UAV utilized many 3D printed items to ease the construction process and lower the cost. This makes the build much more accessible as plans for the 3D prints do not need to be remade, leading to much faster construction. Over the course of the project, we received a lot of feedback from our advisor, Professor Yavas, on what to focus on for the initial design parameters, as well as some manufacturing methods later on. We had originally tried to manufacture each wing as a single solid piece, only to figure out that was mostly unfeasible due to its size. We would go on to manufacture the wing in two separate pieces, with a 3D printed bulkhead for the tail booms between them. The feedback we received would go on to ease the testing process and lead to a much cleaner and more streamlined design.
Important aspect in the design process is project planning as well as its implementation. The project testing for us was comprised of basically 3 different areas: the electronics, a mock wind tunnel, and a glide test. We did a dry test for the electronics where the UAV was grounded, and here we ensured the motor was functional as well as matched the specs provided. We tested the servos by adjusting the ailerons by hand and make sure that they functioned with the servo motors. The mock wind tunnel, here we wanted to simulate a scenario where the fully assembled UAV was subjected to external forces. We did this by having somebody hold the UAV in the back of a pickup truck as we drove it around the block. That way it would be subjected to winds up to about 25 miles an hour. The glide test, here we wanted to observe the glide level as well as the functions of the elevators and ailerons. We had to set a predetermined height and release the UAV and just let it glide without the use of any motor. We came across several challenges during this design. The wing box, for example, it took several iterations to get right. The previous models kept failing and breaking, and we solved this by improving the adhesion and bonding of the 3D print and just getting an overall better print. We also had a wing completely fracture. This delayed our first flight and also caused issues just trying to maintain those same aerodynamic parameters we had before then. We also wanted to apply a coating of fiberglass along the wings for a little extra stability, but unfortunately it didn't bond properly and we ended up using tape, which was a better alternative for that. So that basically covers the challenges as well as the project testing.
Okay, so how does the UAV work? Part 1. The UAV generates lift by virtue of wings. It can manipulate the airflow over the wings to produce higher and lower pressure regions, therefore creating lift and allowing for roll and pitch control. One thing to note with our UAV is that it is what's referred to as a 2-channel UAV, meaning it only has aileron and elevator control. We have dihedral in our UAV to help promote lateral stability, and the communications for controlling the UAV are achieved through an off-the-shelf transmitter and receiver. Initial design. A preliminary requirements diagram was created with MATLAB, then an Excel calculator was made, allowing us the ability to change parameters such as weight, thrust, wing planform, and receive results for lift, cruise, and stall velocities. Our ideal planform was then imported into XFlyer 5 to validate our airfoil selection and our Excel calculations. Finally, this planform was optimized in a final step with a program called ASP, which is an optimization program that works much like a SOLIDWORKS design study. This program then provided us with our final planform and our ideal twist and taperers to achieve the greatest efficiency. The CFD for the plane bodies and other control surfaces were performed with SOLIDWORKS and an online CFD program called SimScale. All of the CAD work for the plane was performed with SOLIDWORKS, and to validate critical components, both hand calculations and SOLIDWORKS FEA was performed for the wing box and wing spars. The fuselage is of a bulkhead/longeron construction containing a carbon fiber bottom skin and a fiberglass top skin. These skins were made using 3D printed molds and a wet layup process. The wings are made of expanded polystyrene, which was CNC hot wire cut, and they utilize a 1/2-inch pultruded carbon spar for strength and wing box mounting. There are 3D printed bulkheads about 14 to 15 inches along the span of both wing halves to accommodate the tail booms. The wing box is a 3D printed structure. Due to the difficulty with performing hand calculations or simulations with 3D printed material which behaves anisotropically, the wing box was heavily dependent on multiple iterations and destructive testing. The final form of the wing box contains a 3D printed structure with aluminum and carbon fiber rod bracing, which is also fiberglass reinforced along the bottom region. The biggest lesson I learned throughout the course of this project is one that I thought I knew before. The lesson being that nothing really goes to plan the first time, and it's necessary to anticipate timely or costly changes. You have to be mindful of this in certain projects, and I will certainly be mindful of this in future work.